Swayam Prabha. Digital India. Educated India.
Okay, so good morning everyone. So we'll be continuing our discussion on depth first search, and we'll look at applications, one particular application of depth first search. In fact, there are several applications of depth first search in particular in directed graphs, and therefore we are also going to look at how this depth first search is useful in directed graphs, and some of the exercises that you have done yesterday can also be done efficiently using depth first search. We will give you pointers to that, the way those can be done efficiently. You may have come up with simple algorithms in yesterday's exercises. For example, for articulation points, for bridges and so on, you may be able to come up with much better algorithms using depth first search, which are quite non-trivial. Okay, so to recall, we have looked at depth first search, which is a way to explore the graph. And again it starts, so we have written it in terms of depth first search of G, and we kept a flag explored of V which was set to false, and then as we keep exploring vertices we keep setting the flag to 1. And we have already analyzed the running time. We have also said that the depth first search, like breadth first search, produces a tree. The two trees can be quite different, and we have analyzed the properties of the depth first search tree as well as the non-tree edges of the depth first search tree. We also assigned what are called as pre-visit numbers and post-visit numbers associated with the depth first search tree, right, or the depth first search of a graph. Now one simple thing in case of undirected graphs is, certainly we can do this depth first search pre-visit, post-visit numbers which are given here. So for example, S was given 1 as a pre-visit number, 2 as a pre-visit number for U1, and then remember that pre-visit number is the first time the vertex is explored during the depth first search. Post-visit number is the time at which we have finished exploring that vertex, that is all its adjacencies have been explored, and that is the number that we give. And we said that we will give actually 2n distinct numbers to different vertices. Every vertex will get a pair of numbers which we call the start and the end of the depth first search for that vertex, right. So you can think of that interval associated with every vertex. Now if you wanted to simply answer this question, that how many connected components are there in a graph, right? This is a simple question. What is a connected component? A set of vertices such that every pair of vertices in that component has a path to each other, right? This is what we want to answer. How many connected components are there? For example, if this was the only graph, there is a single connected component, and if you have a single connected component, in whichever vertex you start your depth first search, you are going to explore all of the component, and therefore there is a single component. So what we said during this pre-visit was that during this pre-visit is we will keep a clock or a counter which keeps on, whenever we assign the number to the vertex, it keeps on incrementing, right. Instead, you for the depth first search or undirected graphs, you could have done something very simple. You could have just kept one global counter which is called the number of connected components. Anyway this loop, the loop here, that is for v belonging to v, this is going over all vertices. So even if there are multiple connected components, it is going to look at every vertex and explore it, right. So therefore if you simply keep a connected component number, so what should you do with this connected component number? You want to assign all the vertices in the same connected component a single number. Let's say that S was the starting vertex, then you give all the vertices here a connected component number, or the number of the component as 1. Maybe if there's some other component, let's say this is another component, then at some point you will go to this vertex and you will start the exploration again, which you should give all the vertices in this connected component as a number 2. So how would you modify this pre-visit of V? You can do a simple modification. What should you do? So you need not maintain, what I am trying to tell is you need not maintain all this sophisticated pre-visit and post-visit. In fact, you can do something simpler. So so you have initialized that connected component number as, let's say, 1 or something. Then every time you go to this pre-visit, you are going to give the value of the connected component number without incrementing it, right? And when do you increment it? Because you want that all the vertices in this connected component should get the connected component number 1. When should you increment this? Sorry? So when do you know that you are actually starting a new connected component? Yeah, please louder. That is correct, but you should tell me in this framework of this pseudo code. So okay, let me just do it here. So I will say that connected component is equal to 1. This is my initialization, right? And this pre-visit of V, I am going to write it here. So I will just write the pseudo code pre-visit of V. So, or connected component number of V is equal to CC. CC is this global variable, right? So now let us look at this. What will happen? Remember that there is also this pre-visit number that we are going to use afterwards. So this, you should not forget that this pre-visit number is something that we have defined and we are going to use it later, but this is only for the connected components number of connected components computation in an undirected graph. So let's see, let's look at the exploration and forget post-visit for now, right? Suppose we do not call this at all. Now what happens? S, when you invoke it, it goes to pre-visit, it gets a connected component of number of 1. When you go to U1, it also gets a connected component number of 1 and so on, right? So you keep doing this as long as you are in this connected component. That is what you would want to do. But you would also want to increment it at some point when you go to this vertex. So when should you increment it? Yes. Correct. Excellent. So now remember that at this for loop is going over all vertices, but okay, so let us do this. So let us see that if okay, so let us go over her suggestion. So we have V belonging to V, you go here at S, and let us say that you have you have given all the vertices in this connected component a component number of 1. Let us say the next vertex in your list that you want to follow is U1. What will you do? So you have finished exploring this, and what should you do now?
So it will come back to U1 only if U1 is not connected to S. Like after we finish if unexplored of S and we go into explore of S, it will go to the next V belonging to V only if that.
Yeah, so which place should I write this connected component plus plus? Yeah, so I'll just give line numbers 1, 2, 3, 4, right? So can you say? Okay, 4. So this is line 3. So if explored of V, if unexplored of V, explore of V, and then CC plus plus, right? So here is where she suggests CC plus plus. Any comments on this? Is it, what do you think? Is it correct? Is it incorrect? So it is just after, I mean, is it in the if or is it after the if? End after, I mean end if. Okay, outside end if. So I'll just write here end if. Okay. So this is okay now with you? Okay. So what happens? Let us analyze this. So whenever we go to the next vertex, let's say U1 is the next vertex. If unexplored of U1, then so this will not pass. Do you see that? And then you will still do CC plus plus. Do you get it? So this doesn't seem the correct place. Any suggestions? Inside if unexplored of V, okay, so we can even start with connected component number 0, that is it is not set to anything, and then he is suggesting that CC plus plus is done here, right? So now let us see what happens. So if unexplored of V, for the first time it is at S, it is going to increment that, and see the connected component number will be set to 1, and then all the vertices we will actually explore. At that time CC has not been modified, and that will be given the connected component number. The next vertex that you will check is possibly U1. For that, explored is going to be set to be true, therefore you will not go inside this if condition, and for all such vertices whichever you encounter, you will not go inside. And then let us say that this vertex is actually U15. At U15, when you go inside, you want the connected component number to be incremented by 1, which will happen here, right. So, I will let you verify whether this is correct, whether this is incorrect, and get back to us what do you think about this, that is this the correct place to add this connected component plus plus. In particular, what we want is every vertex in the connected component should get a single number, whichever number that be, and two vertices, if they are in different connected components, they should get some 2 different numbers. So, how would you answer, are these 2 vertices connected? Just look at the connected component number after DFS has been done. This is a constant time query after this, right. So, this pre-processing of connected components will simply allow you to find one, the number of connected components, and also this answer this query, are 2 vertices belonging to the same connected component, right. So, please verify whether this is the correct place for the connected component increment, right. Okay. So, we will again go back to our old pre-visit thing, and so now we are again saying that whenever we do pre-visit, we are going to do the same thing, that is what we did in yesterday's class, that is we had a global counter which was set to 0 or set to 1, we give that number to the vertex, the pre-visit number, increment that counter. The same counter is used for the post-visit also. So, now this is again in place, and the post-visit, so yeah, so it just says pre-visit of V is equal to whatever counter and counter plus plus, and here post visit is also very similar. I will not write the code, I hope everybody is okay with that, right. Okay. So, any questions still here? So, what we have done is, by a simple modification, we have first found out the number of connected components in the directed in the undirected graph, and also answered these queries after this DFS has been done in constant time, that are 2 vertices belonging to the same connected component. So, all this has been done in linear pre-processing, and then after that you can answer these queries in constant time, correct. Okay. So, now we are going to look at directed graphs and see this the usage of this pre-visit and post-visit numbers, right. So, please feel free to stop me if there are any questions at any point. Okay, so just like in the undirected setting we had tree edges and non-tree edges, here also we will have tree edges and non-tree edges. Let us try to classify tree edges, non-tree edges into different types, because in directed graphs the non-tree edges need not always be back edges, like which were the ones which were completing a cycle, there can be other type of edges. So, let us view a simple example, and now the edges will have a direction. Okay. So, let us simply run the DFS algorithm on this this simple example, right. So, let us see what we get. So, this, okay, so I will just draw the DFS tree here. So, we have A, which will get the pre-visit number of 1, followed by B, assuming that I go to B, that is a choice which I can make, it gets a pre-visit number of 2, then I go to C, I get a pre-visit number of 3, and after this I have 2 edges, I have actually only one edge to explore, which is C to A, and I do not do anything because A is already explored, right. So, now what do you know about this C to A edge? What would you call such an edge actually? Would you have any analogy from the earlier thing? It is actually completing a directed cycle, right. So, we would like to call such an edge a back edge in the graph, right. So, this edge, okay, sorry. So, anyway, I will draw this like this. So, this edge is actually a back edge in the graph. at this point we have finished exploring C because there is nothing to explore more in C, therefore we give it a post visit number which is 4, and then we backtrack and go to B, and what do we find? Do we have anything to explore? No, therefore we give this the number 5. Now we reach A, but A there is something more to be explored, so we go to D and we find that we need to now give a pre-visit number which is 6. Then at D we certainly have this edge, we will explore this edge. Would you want to call this edge a back edge? Okay, what do you want to call such an edge? Yes, it is certainly a non-tree edge, but it is not a back edge. So I will write here that DC is a non-tree edge but not a back edge. Anybody knows a name for this edge? So such edges we are going to call as cross edges, and you can see the name why it is coming as a cross edge. It is a non-tree edge, but it is something it is from an edge which is an edge from a vertex D which is still being explored to a vertex C which has been completely explored by our DFS algorithm, right? And such edges can never happen in case of a undirected graph, because then you would have seen the edge CD itself, right? And this doesn't happen in the case of undirected graph but happens in the case of directed graph. Very good. So now at D we have completed the exploration and we get a post visit number of 7, and finally we are at A, and A there is something still to be explored. What is there? The edge A, from A to C, right? This is still to be explored. What would you want to call such an edge? It looks like a cross edge, right? But it is also slightly different from a cross edge. So I would call this edge, in fact, I mean in the way I have defined it, it is certainly from a vertex which is still being explored to a vertex which has been completely explored. But this is not all the definition of a cross edge. We will clearly say in terms of the pre-visit and post-visit numbers what are cross edges and so on. But this is an edge from an ancestor of the vertex C or an ancestor to a descendant edge, right? And it is from A to C, and we will call such edge as a forward edge. This could have been one of the candidates for being a tree edge if we had actually explored A to C, right? Similarly, this A to, if we had explored A to D first, D to C would have been a candidate for a tree edge. And what finally we will complete this by giving the post visit number of A. Right. So we have completed our DFS exploration. We now have 3 types of or 4 types of edges. So we will call edges which are, there are tree edges, there are forward edges, there are cross edges, and there are back edges, right? So without actually looking at this example and the pre-visit and the post-visit numbers, let us try to make some guesses about what kind of a structure do we expect to see in terms of the pre-visit number and the post-visit numbers of the 2 endpoints of such edges, right? So let us fix a tree edge, right? And a tree edge, clearly we understand what is a tree edge. It is from a parent to a parent to a child. And let's say that if UV was a tree edge, U certainly gets a pre-visit number, V also gets a pre-visit number. What do you know about the pre-visit and the post-visit of pre-visit and of U and pre-visit of V? Difference is 1, very good. But you also know that the pre-visit of V is going to be larger than the pre-visit of U. That is 1, I mean it is just 1 plus, but it is certainly larger. What can you say about the post visit of V and the post visit of post visit of U? Sorry, yeah, post visit of V, right? Why? Because V is going to be completely explored, and then it will be given a post visit number, and then we will give a post visit number to the vertex u, right. So therefore, what do we see about the pre-visit? So I will just write this nesting structure. So this is u, this is v's start, that is pre-visit number, then there is v's post-visit number, and then there is v's there is u's post-visit number, right. So this is the structure you would see, and you can verify that this holds for all the tree edges in the graph. What can you say? So let's go to a back edge first. So again, uv is a back edge. What would you expect the pre-visit number of u and the pre-visit number of v? Yes? Yeah, can somebody raise hands and say? We are interested in knowing what is the, so uv is a back edge. What is the pre-visit number of u, relationship between the pre-visit number of u and the pre-visit number of v? Pre-visit of u is greater than pre-visit of v, right. So I can write that u here and v here, right. This is clear. Now we still need to put the other brackets. Now what can you say about the post-visit of u and post-visit of v? Sorry? At which time? Yeah, we encounter the back edge, we do not know, but what can you say about the, so it will get a post-visit number. It may not be given, that I agree. He is saying that you may not have given the post-visit number when you encounter the back edge, but eventually at some point the post-visit number will be given. What can we say about the post-visit number that u gets? Is less than. So you will see the nesting structure is exactly the other way, that is the u finishes completely first, followed by v, which finishes after that, right, because v is an ancestor of u in the DFS tree that we are constructing, right. So this should be clear. Now let us look at what is a cross edge. So uv is a cross edge. I should have written it like this because these are edges. Yeah, okay. So uv is a cross edge. What can we say about a cross edge? Correct. So we'll have v here and okay. So pre-visit, sorry, say it again. CD is a back edge, but DC is a cross edge. Okay, so what do you want to say? That yeah, but in general I am asking for u and v, what do you want? U is greater than v, so that is what I am writing, right? So v is first and u is after that. What can you say about the post visit of u and v? Yeah, but now we can also ask what can we say about the post visit of v and the post visit and the pre visit of u, right, because this is a cross edge, it is in between these two, right. So we know that certainly a post visit number of any vertex is going to be larger than the post visit of its own the pre visit of its own vertex, but in this case the post visit of v is also going to finish before the pre visit of u starts, and then at some later point this u will get over, right. So this is the kind of so this is the kind of structure that you will see for the pre-visit and post-visit of uv when uv is a cross edge. Finally, I will leave it to you to verify that actually the forward edge will also have the same structure as a tree edge. That is, you will again find the same nesting of the forward edge as the tree edge, but when you are marking the edges which are belonging to the tree, you can easily mark that these are tree edges and non-tree edges. So between the non-tree edges there is a clear distinction. So all the non-tree edges have a different way of the way of the structure of the pre-visit and post-visit. So once you have given pre-visit and post-visit numbers to the edges of the graph, and you have also marked tree edges and non-tree edges. You can look at an edge. If it is a tree edge, you don't have to say anything, there is only one type of tree edges. If it is a non-tree edge, then looking at its pre-visit and post-visit numbers, you can say that whether it is a forward edge, whether it is a cross edge, whether it is a back edge, right? And this can again be done in constant time after you have done this linear time pre-processing. Good. Any questions here? So what we have asked in the undirected setting initially is given an undirected graph, tell me how many connected components are there in the undirected graph. A similar question can be asked about how many connected components are there in a directed graph, right? But this connected components has to be now carefully defined, because the graph is a directed graph. If I have a path from u to v, it doesn't necessarily mean that I have a path from v to u in that graph, right? So now one has to define connectivity in a different way or in a stronger way. So what comes to your mind, when should I say that two vertices are connected in a directed graph? So this is one way, which is a very strong definition. One could have also said that the underlying undirected graph they are connected, but this is what you are suggesting is what is the typical definition of the connectivity, because otherwise you could have as well thought of it as an underlying undirected graph and then done whatever is in, if that suffices for your application. So we will define that u and v are connected in G if there exists a path from u to v and there exists a path from v to u. Yeah, so this is what is our definition of two vertices being connected. So now extending this further, what should you call a connected component? Yes? How would you say that a set of vertices belong to a connected component? When did we say this in the undirected setting? We said that two vertices belong to the same component if they are connected or if they have a path between them. Here we have already said what is connected. So we simply use the same definition that two vertices are belonging to the same connected component if they are connected, that is you can reach from u to v as well as from v to u, correct? So, so let us ask what are the different connected components in this small graph. So are all the vertices belonging to the same connected component? Let us ask this question. Okay, so the question is how many connected components does this graph have, the small graph that I have shown. Okay, so let us verify this quickly. So we want to say that any pair of vertices has a path from x to y as well as from y to x, right, if x and y. So let us say B and D, where you should show me a witness path. So B to D, what is the path? B, C, A and D, that is the path. What about from D to B? D, C, A and B, right? And you can try verifying that this graph does have a single connected component, because A to B you can certainly reach, B to A again you can reach via C, A to C you can reach, C to A you already know that there is a back edge, and so on, right? You can verify it for all pairs and you should do that, but in general we are interested in asking can we find connected components of a graph efficiently, right, of a directed graph efficiently. So the algorithm that we are going to study is a very very interesting algorithm, and it's also very efficient. It makes use of several ideas related to the DFS and the pre-visit and the post-visit numbers. But before we go into the algorithm, we are going to look at the structure of any directed graph in terms of something which is slightly a meta structure, right? Okay.